Welcome to the Arithmetic Zone, and we have another math video. This time we're going to cover partial fractions. So what are partial fractions? Essentially the process of using partial fraction decomposition is taking a complex proper rational function and breaking it down into the sum of two less complex fractions. If you don't know what these terms are, a rational function is simply the division between two polynomials. Usually you see it as a fraction. Now, a rational function is proper if the numerator's highest degree is less than the highest degree of the denominator. So if you look on the left side right here, the numerator's highest degree is 1. Because of this x, the highest degree in the denominator is 2. The numerator's highest degree is less than the denominator, hence this whole function is proper. Same thing right here. The highest degree here, 2. Highest degree here, 3. 2 is less than 3. Numerator less than denominator, hence this is a proper rational function. Now, if that is not the case, then it's an improper rational function. Right here, the numerator's highest exponent is greater than the denominator's highest exponent. And also, if the highest exponents of the numerator and denominator are equal, so let's say this was x squared plus x plus 1, it would still be an improper rational function. Why that matters, we're going to see later. So let's look at our first example right here. X over x squared minus 5x plus 6, and this is an example of using partial fractions for distinct linear factors. The first step you should take when you see a function like this is see if you can factor it out and simplify the process before we even use partial fractions. So right here we can actually use the AM method right here. Set this to A, set that to M. What two numbers add to -5 and multiply to 6? -2 and -3. So we factored out the denominator, and as you can see here, we have two distinct linear factors, x minus 2 and x minus 3. Their highest powers for both of them is just 1, and they are different from each other. Now, if we had two of the same linear factors, then the strategy I'm going to use right here is not going to work, and you're going to have to use a different strategy, which I'll cover in the next part. But for now, let's decompose this rational function using partial fractions. So if you looked at the thumbnail, which I believe this is the same problem anyway, the whole strategy here is to take each distinct linear factor from the denominator and separate them into their own fraction. We're putting the linear factors in the denominator, and then for the numerator, we're going to find these mystery values right here, which are both constants a and b. And whatever we get, this expression right here should be equivalent to our original function. So our next step right here is to get this x right here by itself. So how can we do that? Well, we can multiply all three of these fractions by x minus 2 and x minus 3. And if we do it for all the fractions, then the value of this expression won't change. So I'm going to write it in manually. So x minus 2, x minus 3. And we're going to do it for all of them. So x minus 2, x minus 3, x minus 2, and x minus 3. Immediately you should notice that you should be able to cancel out some terms right here, especially in that last term right here. You can cancel out both the x minus 2 and the x minus 3, leaving out just x. So we successfully isolated the x. Here we can cancel out the x minus 3, leaving just b and x minus 2. And here we can cancel out the x minus 2. So when we cancel out all these terms, what we're left with is a times x minus 3 plus b times x minus 2 is equal to x. So now what we have to do to find a and b is to find ways to find and substitute values for x so we can find one at a time. So the key here is to find values of x that get rid of one of the a or b values, usually by having it multiply with 0. So our first way of doing this, if you notice right here, if x is 3 right here, then 3 minus 3 is 0. A times 0 is nothing. Then we can find what b is. So let's set x equal to 3. Substitute 3 for all values of x in this expression as such. So 3 minus 3 is 0. 0 times a is nothing. So delete that, and then b is equal to 3, because 3 minus 2 is just 1. 1 times b is just b, and b is equal to 3. So we successfully found b. Now we have to find a. So how can we get rid of the b term? Let's substitute 2 for x. So let x equals 2, and we substitute 2 for each value of x. And now we get rid of this b term right here. And now what we're left with is negative a is equal to 2. But we're looking for a, not negative a. So multiply the negative on both sides like that, or divide by negative 1, and you get that a is equal to negative 2. So once you find these values, what do you get? Well, you put them back into our original expression that we found over here, and you should get that negative 2 over x minus 2 plus 3 over x minus 3. And these decomposed fractions, the sum of them is equal to this original function right here. So why would you ever want to do this? Well, aside from the fact that you can make the fractions you're dealing with a little simpler, this is especially useful if you're trying to integrate. So imagine if this was an integration problem right here. So I write the integral sign, put in dx, and if you try to integrate this, you notice that it's actually pretty hard. You can't use u sub because the denominator has the higher power over the numerator. So what you have to do in this case is you have to use partial fraction decomposition to break this down into simpler terms. And now essentially we're taking the integral of this, and this is much easier right here. We have two constants in the numerator, and then linear factors for the denominator. And if you were to integrate this, you would get that it would be negative 2 ln of x minus 2 plus 3 ln of x minus 3 plus c. Pro tip, if you ever see a constant over a linear factor being added or subtracted by something in the denominator like this, then it's very easy integration. It's just the numerator as the coefficient ln of the denominator. It's true for all cases of that. Now let's look at another example of distinct linear factors. 3x squared plus 4 over x cubed minus x. This one's a little harder. So again, the first step is to factor out the denominator. So first step, we can factor out the x. And so we get x times x squared minus 1. But we can also factor out x squared minus 1 even further into x plus 1 and x minus 1 using a strategy called difference of two perfect squares. So if you notice right here, we actually have 3 distinct linear factors. And again, they have to be different from each other. If they're not, then this strategy will not work. And also, if this was x squared plus 1, then this would just be a quadratic factor. It wouldn't be a linear factor, and you'd have to use another strategy to solve that issue. So once you get it into this simplest form right here, you apply the partial fraction decomposition principle, in which you, for every term in the denominator, you make it its own separate fraction as the denominator, and then you'd have to find the mystery values for the numerator. So this time we have 3 distinct linear factors instead of 2, so we have a, b, and c to find out. So again, what do we want to do? We want to isolate the numerator. So how do we get rid of all this? We have to multiply by x, x plus 1, and x minus 1 for every single term. So this is going to take a while to write, but it's easier to visualize this way. Too bad I don't have any space though, so it's going to look really bad. So bear with me. I'm writing it at the top. It looks so bad. But you know what I mean. We're trying to multiply all these terms. So now we want to cross out any terms we can. So usually for the original function, you should be able to just cross out all the terms. So as such, we're left with the numerator. Here we can only cross out x minus 1. Here we can only cross out x plus 1. And for the a term, we can only cross out the x. So we're left with this ugly expression right here. But when you put it all together, you should get it as a times x squared minus 1 plus b times x minus 1 plus c times x plus 1 equals the numerator of the original function. Why is it x squared minus 1 times a? Well, remember, we were left with x plus 1 and x minus 1. And we got those two factors from this quadratic factor right here, x squared minus 1. So I just simplified it like that. Now we want to solve for a, b, and c. So you should be able to immediately notice that b and c are both attached to a lone x. So if we substitute x for 0, we can just eliminate both of those immediately. So let's do that. Let x equal 0. We substitute 0 for each value of x. B and c, both of those terms get washed out, and we're left with a and the right side of the equation. We're left with negative a is equal to 4. We're looking for a, so a is equal to negative 4. Now how do we find b and c? Well, if you notice a, this x is being squared. That means we could have both a positive and a negative number right here. Make this whole term equal to 0, and that'd be positive 1 and negative 1. So we have some flexibility there. So let x equals 1. If we let x equal to 1, 1 squared minus 1 is equal to 0, so that term gets eliminated. And right here, 1 minus 1 is also equal to 0, so that term gets eliminated. So we're left with c. So we're left with 2c is equal to 7. We have to divide 2 on both sides to get c is equal to 7/2. Don't be alarmed by the fact that you have a fraction as one of these as one of the numerator terms. It's actually pretty common, and we were lucky that we didn't see any in the last example. Now finally we have to find b. So again, we could use negative 1 to eliminate a and also to eliminate c. So let x equals negative 1. If we were to substitute negative 1 for each x value, this term gets eliminated and that term gets eliminated. So we're left with b. 2b is equal to 7. b is equal to 7/2, just like c. So now put all the a, b, and c values together into this original expression, and we get then negative 4 over x plus 7/2 over x plus 1 plus 7/2 over x minus 1. This whole expression is equal to the original function. And again, if you were integrating, which is common, if you were integrating this would just simply turn out to be negative 4 ln of x plus 7/2 of ln of x plus 1 plus 7/2 of ln of x minus 1 plus c. This little shortcut I told you about the ln still holds true even if the numerator is a fraction. Just make sure that the numerator is a constant and the denominator is a linear factor, being added or subtracted by a value or just by 0. So anyway, we're going to move on to our final example for today, which is actually pretty simple. This time we're not dealing with distinct linear factors, but we're dealing with improper rational functions. So if you notice in the previous two examples, both of them were proper rational functions. The highest power of the numerator was less than the highest power of the denominator. That is not the case here. The highest power in the numerator is greater than the highest power in the denominator. And when you see this and you want to decompose this fraction, we can't use partial fractions. Instead, we have to use long division. So let me set this up for you. X cubed plus x plus 1 being divided by x squared plus 1. How does this work? Well, focus on the highest power here. How many times does x squared go into x cubed? Or rather, what value being multiplied to x squared equals x cubed? Just multiply x squared by x. So x times x squared is x cubed, and we want to subtract that. And x times 1 is just x. Got to subtract the x, so this gets canceled out and this gets canceled out. We're left with a 1 that drops down, and we can't really do anything about this 1. So this is actually our final answer. Not for this whole equation, but it's our final answer for this long division with the 1 acting as the remainder. And when you have a remainder of a rational function, you take the remainder and divide it by the divisor. So this should be equal to x plus 1 over x squared plus 1. And this is actually the furthest we can decompose this because this is a quadratic factor. And we haven't covered how we can decompose that yet. But again, if you were integrating this function, well, we can't use any of those ln rules because this is a quadratic factor and this is just x by itself. So but this is actually a special identity, not really that special, but it is pretty recognizable. It's just tan inverse of x, then this is just half x squared. Add all this together plus c to get our final answer if you were trying to integrate it. So that's partial fractions for you. In the next video, we're going to look at those extra cases I was talking about earlier. See you then.